Assalamu alaikum warahmatullahi ta'ala wabarakatuh. I'm Salma Al-Mahdi, and today we are going to discuss metabolism of pyrimidine nucleotides. Our objectives are to list the common precursors in purine pyrimidine biosynthesis, to state the significance of compartmentalization of carbamyl phosphate synthase 2, describe synthesis of pyrimidine deoxynucleotides, describe pyrimidine salvage pathway, describe regulation of pyrimidine biosynthesis, to list the main metabolites of pyrimidine catabolism, list examples of drugs that inhibit pyrimidine biosynthesis, and list relevant disorders. Regarding pyrimidine biosynthesis, there are common precursors that are shared between synthesis of both purines and pyrimides, and these include 5-phosphorhydroxide 1-pyrophosphate, amino acid glutamine, carbon dioxide, amino acid aspartate, tetrahydrofolate, ribose phosphate. However, ribose phosphate comes early on in purine biosynthesis and late as a late reactant in pyrimidine biosynthesis. The first reaction of pyrimidine biosynthesis is a condensation reaction of glutamine, ATP, and carbon dioxide, which reminds us of the first reaction of urea synthesis. In fact, this reaction is catalyzed by a similar enzyme that is called carbamyl phosphate synthase 2. However, this enzyme is distinct from the mitochondrial carbamyl phosphate synthase 1, which is active in urea synthesis. Thus, compartmentalization provides separate flows of carbamyl phosphate, separating carbamyl phosphate 1 from carbamyl phosphate 2 because it shares the same substrate. Helps in dividing or in partitioning two pathways for carbamyl phosphate. One for distinct for urea synthesis as a metabolic pathway in amino acid metabolism, and the other one is a purine synthetic pathway in pyrimidine synthesis. So this condensation reaction forming carbamyl phosphate followed by a second condensation reaction, which is also similar to urea cycle. Carbamyl phosphate condenses aspartic acid to form aspartate transcarbamylase, and then the ring closure is loss of water forming dihydroorotic acid. So the ring is now formed. This is followed by dehydrogenation, where the hydrogens are taken up from carbons of dihydroorotic acid or dihydroorotate received by NAD to form NADH, catalyzed by dihydroorotate dehydrogenase to form orotic acid. And this is followed by phosphorylation, transfer of ribose phosphate moiety from PRPT to orotic acid to form orotate monophosphate. And then orotate monophosphate form uridine monophosphate UNB by a decarboxylation reaction. This is followed. If you want to form UDP and UTP, this is done by two consequent steps of phosphorylation by kinases from UNB to UDP, from UDP to UTP by another kinase where the source of phosphate is ATP. The next reaction is amination reaction, whereby glutamine is the source of the N-nitrogen to form CTP. Reduction of CTP by ribonucleotide reductase forms deoxyuridine diphosphate, DUDP, which is used for, of course, for substrate for the second kinase. It has one of two reactions, either a kinase here, where ATP is the source of phosphate to form deoxyuridine triphosphate, or it can be hydrolyzed to form deoxyuridine monophosphate. So the diphosphate can be triphosphate or can be a monophosphate with loss of inorganic phosphate. Methylation of deoxyuridine monophosphate forms deoxythymidine monophosphate by thymidylate synthase, and this is the only reaction in pyrimidine biosynthesis that requires a tetrahydrofolate derivative, namely N5N10 methylene tetrahydrofolate to form deoxythymidine monophosphate. In humans and other animals, 5 out of the first 6 enzymes of pyrimidine biosynthesis are arranged as multifunctional polypeptides, similar to the polypeptides that we have come across, such as fatty acid synthase, if you remember. The exception is dehydroorotate dehydrogenase is singular or present as an individual enzyme. CAD polypeptide includes 3 enzymes: carbamoyl phosphate synthase plus aspartate transcarbamylase plus dihydroorotate. UMP synthase, a bifunctional enzyme which includes 2 enzymes: rotate phosphoriboside transferase and OMP decarboxylase. And you know the benefit or the advantage of having such a lignin. We have already discussed it. Regarding drugs that can affect pyrimidine biosynthesis, one of the most important examples is methotrexate. Methotrexate is used in treatment or management of malignant conditions as well as inflammatory conditions such as rheumatoid arthritis, for example. Methylation of the step in which there is methylation of deoxyuridine monophosphate to form deoxythymidine monophosphate is the only reaction, as we said, in pyrimidine biosynthesis that requires a tetrahydrofolate derivative. Methylene is reduced to methyl and tetrahydrofolate is oxidized to dihydrofolate. Tetrahydrofolate then must be regenerated by dihydrofolate reductase, which is inhibited by methotrexate. So methotrexate inhibits the reformation of the reduced form of tetrahydrofolate, which is needed for the reaction of formation of deoxythymidine monophosphate. Dividing cells are especially sensitive, hence it is used as an anti-cancer and anti-inflammatory drug. So we said the formation of thymidine monophosphate from deoxyuridine monophosphate requires thymidylate synthase, which uses tetrahydrofolate in the reduced form from dihydrofolate. This reaction from deoxyuridine monophosphate to thymidine monophosphate requires tetrahydrofolate in the reduced form, in the form of 5,10 methylene tetrahydrofolate. So when it is used, we get dihydrofolate. To regenerate this step, this form of folate again, we need folate reductase. Folate reductase is the one that is the target for methotrexate. So through this, methotrexate stops formation of thymidine monophosphate, it stops formation of nucleic acid, and stops or impairs regeneration or division or production of new cells, whether these new cells are in an inflammatory process or in a cancerous malignant process or neoplastic process. 5-fluorouracil is a pyrimidine analog. It is converted by salvage pathways to fluorodeoxyuridine monophosphate, which binds to and inactivates thymidylate synthase. So it is used as a chemotherapeutic agent. Regarding salvage pathways of pyrimidine, few pyrimidines are salvaged, unlike pyrimids. 2 pyrimidines, ribonucleosides, are converted to corresponding ribonucleotides. So from uridine to uridine monophosphate, from cytidine to cytidine monophosphate. And 2-pyrimidine deoxyribonucleosides are converted to corresponding nucleotides. The thymidine to thymidine monophosphate, deoxycytidine to deoxycytidine monophosphate, and by corresponding kinases. Regulation of pyrimidine biosynthesis can be through allosteric mechanisms, particularly the first two enzymes. Carbomoyl phosphate synthase 2 is inhibited, allosterically inhibited by uridine triphosphate, UTP, and purine nucleotides, and activated by PRP3. Aspartate transcarbamylase is inhibited by CTP and activated by ATP. Pyrimidine biosynthesis is also enzymes are subject for induction repression, of course, at the genetic level, particularly the first three and the last two enzymes. Purines and pyrimidine synthesis are coordinately regulated mole for mole through the PRP3 synthase. It is important because building up of nucleic acid requires equal molar amounts of purines and pyrimides. And this is just to show you the regulation of particularly the role of PRPT, where it is inhibited by, for example, thymidine monophosphate, and the PRPP itself activates pyrimidine biosynthesis, the formation of carbomoyl phosphate, and the also UTP, CTP, both of them has negative feedback on the early pathway as well as in the early step formation of carbomoyl phosphate molecule. So how are pyrimidines catabolized? Catabolism of pyrimidines produces water-soluble metabolites, carbon dioxide, ammonium, beta-alanine, and beta-amino isobutyrate. Unlike purines, which produce uric acid that is water insoluble or has a tendency to precipitate in tissues and to form crystals and stones in the renal system or in the kidneys particularly. Increased excretion of beta-amino isobutyrate is increased in conditions that associate with increased DNA destruction, understandably, such as leukemia and severe X-ray radiation, and in conditions in which there is a recessive genetic abnormalities. Beta-amino isobutyrate may be transaminated to methyl malonate, semialdehyde, and then to succinyl-CoA. Can be an intermediate in citric acid cycle. What about cytosine? Deamination of cytosine to uracil, followed by reduction to dihydrouracil, hydration to beta uridopropanate, hydration and breakdown to beta-alanine, carbon dioxide, and NH3. So this is cytosine, this step of breakdown into carbon dioxide, NH3, and beta-alanine. Of thymine, thymine first reduced to dihydrothymine, hydrolyzed to beta-uridoisobutyrate, and then hydrolyzed to carbon dioxide, NH3, and amino isobutyrate. Disorders that are related to pyrimidine metabolism include beta-amino isobutyric aciduria, which, as the name implies, the presence or increased excretion of beta-amino isobutyric acid in urine. It is an autosomal recessive condition. It is generally asymptomatic but frequently encountered in patients. The deficiency is of transaminase. Orotic aciduria. There is orotic aciduria type 1 and type 2. Type 1 is due to deficiency of orotic phosphoriboside transferase and or delayed decarboxylase. So the consequences will be orotic acid crystalluria, crystals of orotic acid, failure to thrive, and megaloblastic anemia, large red blood cells, immature blood cells, immune deficiency, remission occurs with oral and supplementation of uridia. It is also autosomalysis. Orotic aciduria type 2 is due to deficiency of orthidylate decarboxylase. There is orthidiniuria, so the presence of orthidine in urine, orotic aciduria, presence of orotic acid in urine, megaloblastic anemia as well. Remission is also with oral supplementation of uridia. Ornithine transcarbamylase deficiency is a form of protein intolerance, present as protein intolerance, hepatic encephalopathy